Your new friend, the Mole, and I are happy to see you again. What's that, Mr. Mole? Oh, you want to have some fun today? Sure. We can have some fun with chemistry math as we learn to calculate percent compositions and empirical formulas. Mr. Mole says, fasten your seatbelts for this one, kids.
In this lesson, you will calculate the percentage by mass of an element in a compound, define empirical formula, and determine empirical formulas.
I hope you had fun calculating the percentage of sugar in your gum samples. Oh, good bubble, Mr. Mole. There are times when it is useful to a chemist to be able to determine the percentage of a certain element in a compound. The easiest way to learn this is to dive right in and do an example. Let's find the percentage by mass of oxygen in water. It is really just the same as your gum experiment. To determine the percentage of sugar in your gum, you needed to know two things: the mass of the sugar and the mass of the whole piece of gum. This is the same for any percentage calculation. We always need to know the mass of the part and the mass of the whole. So, to find the percentage of oxygen in water, we need to know the mass of the oxygen and the mass of the water. We could do this by experiment, but we can also do it using molar masses. A water molecule contains 2 hydrogen atoms for every 1 oxygen atom. Hydrogen has a mass of 1.0 grams per mole, and oxygen has a mass of 16.0 grams per mole. We add these together to find the molar mass of water and get 18.0 grams per mole. Now, to find the percentage of oxygen in water, we take the part that is oxygen, 16.0, and divide by the total mass of 18.0, and then multiply by 100%. Our final answer is that water is 88.9% oxygen. As you can see, now that you are experts at finding molar masses, percentage compositions are going to be easy. Let's just jot the steps into our notes.
To calculate the percentage by mass for an element in a compound, you divide the mass of the element in the compound by the total mass of the compound and multiply by 100%. When asked to find the percentage composition for a compound, this procedure is followed for every element in the compound.
Now, let's do an experiment to determine the mass percentage of carbon in sodium bicarbonate, otherwise known as baking soda. We will then calculate the mass percentage using molar masses and see how the two compare. Your local teacher is going to give you a lab sheet so you can fill in the data as we do the lab. Then, we will work on the conclusion questions together.
The students are using the digital balance to find the mass of a sample of sodium bicarbonate. The students tare the balance with the massing cup before adding the sample. They find the mass of sodium bicarbonate to be 0.23 grams. Now the students use a funnel to put the sodium bicarbonate into a pipette. The students also have a pipette that contains hydrochloric acid. The students put both pipettes into a beaker and find the mass to be 5.98 grams. This is the mass before the reaction takes place. The students add the hydrochloric acid to the sodium bicarbonate and observe the reaction that takes place. They continue to add hydrochloric acid until there are no more bubbles. Now that the reaction is complete, the students put both pipettes back in the same beaker and mass again. The mass after the reaction is complete is 5.85 grams.
Now, we are going to look at the calculations using this data. First, we need a balanced equation for the reaction that took place.
Sodium bicarbonate reacted with hydrochloric acid to produce sodium chloride, carbon dioxide, and water. Take a minute to copy this equation into your lab sheet and balance it. You should have figured out that the equation was already balanced. Look at your products. Which one was bubbling away? Of course it was the carbon dioxide.
Now, it is time for you to work on the conclusion questions. First, you want to calculate the mass of carbon dioxide produced in the experiment. Then, you want to calculate the percent of carbon in carbon dioxide using molar masses. Next, use these two pieces of information to calculate the mass of carbon in the carbon dioxide that bubbled away. And finally, calculate the percentage of carbon that was in the original sample of sodium bicarbonate. Your lab sheet guides you through these calculations. Local teachers, please pause the tape for your students to complete the calculation section of Lab 1. Oh, you're done. Then your class must have determined that the sodium bicarbonate used in the lab is 15% carbon by mass. Now, let's calculate the percentage of carbon in sodium bicarbonate using molar masses and see how the two compare. Remember that the formula for sodium bicarbonate is NaHCO3. The molar mass of sodium is 23.0 grams per mole. Hydrogen is 1.0 grams per mole. Carbon is 12.0 grams per mole. And oxygen is 16.0 grams per mole. Calculate the percentage of carbon. If you worked it correctly, you divided 12.0 by 84.0 and then multiplied by 100% to give you 14.3% carbon in sodium bicarbonate. So our lab data gave us 15% and molar masses gave us 14%. Is this acceptable? It is. Remember that there is always going to be some experimental error when performing a lab. Your local teacher is going to pause the tape for you to discuss possible types of experimental error in the baking soda lab. Please pause the tape now for discussion. How about one more example, just to be sure you've got it, before we move on to something else? Let's find the percent composition of aluminum oxide.
Complete this problem in your notes. The first step is to write down the formula for aluminum oxide. Al2O3 is correct. Now you will find the molar mass of the aluminum, the oxygen, and the aluminum oxide. Check your work. Since the problem asks you to find the percentage composition, you need to find the percentages of both aluminum and oxygen. To find the percentage of aluminum, divide the part that is aluminum by the total and multiply by 100%. To find the percentage of oxygen, divide the part that is oxygen by the total and multiply by 100%. Finally, check your work.
You will continue to practice calculating percent compositions after you finish viewing this program. For now, let's calculate an empirical formula using percent composition data. From the confused looks on your faces, I guess we better back up and define empirical formula.
The empirical formula of a compound expresses the simplest whole number ratio of elements in that compound.
So, let's try an example. The percentage composition by mass of a compound is 56.6% potassium, 8.7% carbon, and 34.7% oxygen. Let's assume that we have 100 grams of our compound just to make things simpler. That means we have 56.6 grams of potassium, 8.7 grams of carbon, and 34.7 grams of oxygen. Your local teacher is going to pause the tape while you convert the grams to moles. When that is done, we will be able to determine a ratio of the elements in the compound. Local teachers, please pause the tape while your students make these conversions.
Check your work to be sure you correctly converted your grams to moles. Since moles are just a way of counting atoms, we can use these numbers as the subscripts for our formula. That gives us K 1.45, C 0.73, O 2.17. Now that's a funny looking formula. Look at the definition for empirical formula again. It's the simplest whole number ratio of the elements in the compound. To convert our values to whole numbers, we need to divide each subscript by the smallest subscript. In this case, 0.73. This gives us an empirical formula of K2CO3. I'm sure you remember that this would be the formula for potassium carbonate.
Sometimes, empirical formulas seem kind of tricky, but once you get some practice, you'll see that it's just an application of stuff you already know. Let's do another experiment and use it to practice writing an empirical formula.